Okay. Ready to go?
Yes, sir.
All right, here we go. All right, hey everybody, I'm Marco Perry. I'm a founder of Pensa Labs and Pensa, and I'll walk you through a little bit of that. I'm super excited to have the opportunity to speak here today. Thank you to the ORG organization, and I'll walk you through it. I got an hour. I know I'm keeping you from beers and drinks, so I'll try to keep it as tight as possible. But it does give me a lot of time to tell you a little bit about my perspective on how this stuff works. So the general talk is the automation without regrets, right? So I'm gonna walk through maybe like 6 chapters, try to make it as quick as possible again. Where I see the gap in digital fabrication is. In digital fabrication, I think when you think of automation in this case, I'm not just talking about wire benders. There's 3D printers, there's metal printers. Even there's a whole bunch of different classes of printers. There's CNC machines, et cetera, right? So within that, where are the gaps and where do they come from? And then how did we get to now? Which I think it's kind of important to frame it from this perspective. And then the transition to a digital ortho lab, what happens there, and then try to find a good fit. And then some key takeaways. So what do I really mean by automation without regrets? Not even one letter. No regret at all. So you want to have an improvement, right? Obviously, without increasing complexity. Because what's the point if everything just gets more complicated, right? And then you want to reduce dependencies on this scarce expertise, because that's the whole point here too, right? Everybody's telling us that they're having a hard time finding qualified, skilled people to work. And if you replace them with somebody who has to be qualified and skilled at something else, still the problem, right? Deliver ROI across the whole entire workflow. So the things like a wire bender are just the beginning of the workflow. So how does it affect and unlock everything after that and scale with your business? And just being mindful not to over-automate. So there's a lot of examples of this, for example, in the automotive industry, where they automate everything and then they build fragile systems, because what if this one key component goes down? Now the entire line shuts down. Now everybody's sitting on their hands rather than producing, right? And you don't want to create new bottlenecks or replace old bottlenecks with new bottlenecks. So where am I from? So Pensa Labs is an offshoot of Pensa. So Pensa is a 20-year-old design and innovation company. I founded that one as well. We design just about everything. So we have industrial design, engineering, research strategy, packaging, branding, apps, cloud-based. We do medical products. We do bags for dogs, but we also do bus shelters and blood glucose monitors and healthcare devices, vending machines. And within that, one day we were designing this chair, and it was for a well-known office furniture brand, and we were able to iterate really quickly on the shell of the chair, because those are 3D printable, right? But then we noticed we just couldn't make the wire. You couldn't really 3D print that wire, right? So there's this gap in digital fabrication that exists, and I think you guys are experiencing it as well. There's a lot of technologies in an additive space. You can grow apart. There's a lot of technologies in the subtractive space. This is a machine that we've used to carve out that shell of the chair. We made it full scale with a machine like this. It's basically a welding robot from the automotive industry, and you stick a very powerful router on it, and it carves out your chair. But then when it came to the frame, I had to go to like a guy who made bikes or a guy who could make jigs, right? It was this last mile, which is all to say that we like to go through a lot of prototypes in the industry of industrial design and engineering, because we're testing things all the time. And as famous physicist Richard Feynman says, if you can't create it, you can't understand it. And I truly believe in this, and this is what we try to do all the time. So we made one. That's how we got here. We made the one on the right. It was made out of leftover parts from a vending machine that we were working on, and it kind of worked. And then we kind of made slightly better ones and slightly better ones, and we just made them for ourselves, honestly. Then people needed them, so we started providing them to schools and universities, and we kept on hearing the same thing, that there's this gap in this linear wire form stuff. So we kept at it. And we started Pencil Labs, which sold these tiny machines first, and now on the floor you can see the larger ones. And these were really made to learn more and more about this space, and we learned a lot about the orthodontic space in that, and also medical, spinal, aerospace, because they all have a shared problem, which is, how do I make the wire? So, speaking of making, let's just take a step back and think about how things were made and why this is important. I guess this is really coming from the industrial design perspective. So back in the 1800s, you would make a chair like this, like Shakers. And then in the 50s, you had like these kind of chairs. So before the industrial era, it was craft. So craft was, there was a skilled craftsman sitting there carving away, making a chair, and they were really good at it. But because they were making a chair, they could make a bespoke chair. You want a smaller chair, you want a bigger chair, you want a double size, you want a love seat. It doesn't really matter. They're carving it one by one. They can make whatever you want. And then in the 50s, which sort of really came out of the Henry Ford industrial era, was you could make a more mass-produced chair. So this chair is the diamond chair by Henry Bertoia. And Bertoia was a sculptor. And if you look at it, and you guys are all wire people, otherwise I doubt you'd be here, is that every single one of those wires is unique. And that makes this chair really expensive. So it's like $2,000 for one. And not just because it's Henry Bertoia's chair, but because the fabrication is the bending and the skilled laser welding. Today it's laser welding. In the 50s, it was manual welding. And it's beautiful, and it's difficult to sort of like crowbar industrial scale production with this bespoke craft. And that's what makes it hard to make. But Bertoia got exactly what he wanted because he was an artist, right? And then the other chair, to the contrast, that came out about the same time. This one's designed by Charles Eames. Charles Eames is a very famous industrial designer. In my world, he's like one of the GOATs. And the way they make this chair, because he's an industrial designer, he's designing for industry, is he went to a shopping cart factory, and they pump out a grid, they weld it all in one shot, and they stamp it into the shape. So the Bertoia chair costs more to make than you can buy an Eames chair, but they're both beautiful. So what happened is industrialization started to take over. And so this standardization of everybody gets the same thing, any color you want as long as it's black, is sort of Henry Ford's quote, comes at a cost because you can't get just exactly what you want. So in the 2010s, really like 1986, Chuck Hull invented 3D printing. And in 2004, Patrick Joine, I forget how to pronounce his name, he created the first 3D printed chair. So the excitement about 3D printing was you can get the craft, you can get the bespoke, you can get exactly what you want. Personally, I don't want this chair. It looks really ugly and uncomfortable. But you can get it if you wanted it. And so you get that bespoke, but you get the industrial scale. You don't need the craftsman that was first an apprentice and then a journeyman and then a master craftsman. You could just print it. So you get the best of both worlds. You can get craft and you can get industrial scale. And Neil Gershenfeld, who's very prominent, is sort of, again, one of the GOATs, he said the consequences is that everything will be personalized and you can make almost anything anywhere. So if you can see where I'm going with this, it's like you can't do what Eames did with a chair to an appliance because they're patient specific. you need something that can give you we have issues in the craftsmanship because you need the perfect, well-crafted device coming from a master craftsman, but we want to take advantage of some of these technologies, right? So it created this is a well-known thing called a hype cycle with 3D printing in particular, where it's like, oh my gosh, I can bespoke output is now easy, right? So everything is awesome. It's going to be awesome. So in 2010, everybody got a 3D printer, right? So like people at home could 3D print their broken dishwasher part, or people at home could make just the right pencil cup. And everybody was so excited about this, and everybody got 3D printers. And then pretty soon after, it's called the trough of disillusionment, right? Which is like, I think some people may have even experienced this with some of the automation that you see in the ortho world, right? Where like, sure, maybe I can print stuff, but it's actually sometimes much harder to do to get that part out to be useful than it is to just make it by hand. And oftentimes, it's worse, right? The resolution is bad, the strength is not as good, et cetera. So oftentimes this sort of CAD creation was an issue with 3D printing where, you'd have to then become really good at CAD. So it's like, well, I could either learn to carve something or I can learn to CAD something, and they're kind of the same amount of time. So like, what am I trading? And then now I have this new bottleneck because I've just sort of traded the one bottleneck for the other. And then ultimately technologies will evolve and you go through this slope of enlightenment and the plateau of productivity. So that's where I believe we're kind of here, where none of these technologies are really useful until you can go through this sort of art to part problem. Like, how do I create the part to then how do I create the art to create the part? And if I can make that simple and easy. So what changed in ortho was that scanners became smaller, they became easier to use, they became less expensive, they became more adopted. And then in doing so, you could, instead of shipping molds and impressions, which are HIPAA compliant, right? So like you have to store them because those are records. Now you could just store files, and then you can communicate better because you could send them at the speed of the internet, right? And then all of a sudden, this unlocked all sorts of opportunities in the dental space, in the orthodontic space, reducing cost, time. But we're back to the same problem that I had, which is it was a quick and easy translation of this to go into additive manufacturing because you just basically had the same file format and you hit print and it bases it and it prints it. Or subtractive, you can put in material and machines it out. And sure, there's some CAD programs that you have to go through or CAM programs to go through, but these existed from other industries, so it was a direct translation. But informative in being able to bend stuff, you still don't have equipment, which was the same problem I had. So this is where like the two kind of merged. So what people need or needed and still do is this easy input that gives you that craft level of flexibility, but also the print level simplicity with master quality level, right? And you still need industrial scale output, but low commitment. And what do I mean by low commitment? It might be price, it might be size, it might be dedicated technician, it might be, oh, I need 220 power, or I might need 110 PSI to run the compressor, to run all the solenoids in there. So in doing that, you really have to think about like what's the total commitment of translating to this equipment. So what are your options? So at the beginning, right, you had two options. You have industrial scale machines and you have hand bending. Industrial scale machines are really good at making the same thing over and over and over as quickly as possible. Things that make paper clips, little springs, things like that. But they're extremely high price point. This is like a $250,000 machine. They take a lot of time, they take a lot of space, they take special power, they take a special technician, and so you have this high commitment. Or you have hand bending, which is very adaptable. The human hands can build whatever you want, right? but it's difficult to attract and retain talent. There's high training time, there's high labor costs, and there's limited output and speed and repeatability, right? So that was the options. So when you look at the 2x2 graph, one is like there's a high volume production, a low volume production, and then low mix means every part is the same, and high mix means every part is different. And there's often stuff in between. So industrial machinery is really good at the upper left-hand quadrant, and hand bending is really good at the low right-hand quadrant, but ortho space is more and more is growing into one of the higher mix, but also higher volume. So in doing that, how do you go from the low volume into higher? Well, you got to just add people, right? And that means you have to add training time, and you have to add capital and retention. And in industrial machinery, if you want to go into the ortho space, then we have to make that machine easier to use, easier to set up, less commitment in time, space, training, etc. And you have to eliminate this programming because, for example, I talked to somebody who runs this machine. I was like, oh, this is a very nice spring. How long did it take you to program it? He's like, oh, this one's about 7 days, but this one could be like 4 weeks, per part. But then you just turn it on and lights out for 365. That's all it's doing. So they don't really care about that commitment. But this is not the case in ortho, right? So that's where these sort of formative benders are coming in. This is why they're coming in, because the goal is it should be able to make a part as quickly as a person in total, but anybody could use it, right? So what happened? So now we start getting equipment being introduced, but what we've heard is we're kind of in that trough of disillusionment because the software is a little clunky, a little bit buggy, hard to use. Technicians, they can get some shapes, but they don't get all the shapes that they want. Their machines are dedicated to one size wire. Some machines we've seen, like you'd have to change the entire machine to change the wire size. And ultimately, everything that's a little bit complex, it's not standardized, goes back to the craftsman. So it's like a half solution. So how do we get out of this? Well, one is you got to start with training. You got to reduce training time. So when you're looking for a machine, if you feel like, oh, we're going to have to spend some time really getting to know this, and then you'll get that one person who's really good at it, well, you kind of have the same problem, except now it's the digital versus the physical, right? Because that knowledge is now locked in that individual, and that becomes yet another operational risk, because now this is the only guy who knows how to run the machine. So we sell machines in very different industries, but we get the same comments from aerospace. In aerospace, it's like, Joe really knows how to run the machine. He's 75 and retiring, and he really would kill us if we tell him to come back and fix it. And so you don't want to just trade those things. The other thing is you want minutes of training, not months of training. And you want a low dependency on this expert level, and you want hardware and software that just works. Because and I can look at equipment, I could tell you all the sort of mathematical and physical reasons why it might not be working, but that's not your industry, and that's not your problem. Or it shouldn't be. The other thing is you want adaptability to all the different cases, which is there's lots of shapes. There's many shapes in one part. There's many wire diameters, often 2, maybe more. So many cases have all these requirements, and you're going to need some sort of piece of equipment that can handle that for it to be useful. I mean, there's plenty of them that can handle less, but it becomes a lot more useful if you can do these. And these are not, by the way, our images. This is NeoLab. They send me some screenshots of the stuff that you guys are making. So this is the kind of stuff they're making. And it's really impractical to say, okay, I want to run 032, now I want to run 028. Okay, we're going to need a tooling change, we're going to need a spool change, we're going to have to set up the straightener again, we're going to have to recalibrate this material, and then we can get going. It's like, well, now we've just interrupted the flow of the lab again. So you really have to think about how do we accommodate all these variety of cases, variety of wire sizes. We have sharp bends, we have smooth bends, or sharper. Ben's typo. But you know, like for us, like from an engineering perspective, this sharp shape and this smooth round here to one big smooth shape, that's actually really hard to do. You wouldn't think so, because the humans are good at it, but machines are not. And you want to make whatever you want, right? So one of the reasons this is tough is because if you really think mechanically, machines really move in X, Y, Z, like they move in a cubicle. And computers are really good at that. And the mouth is an organic shape, right? It's completely incompatible with the way computers work, the math works, the motion of the motors. But there's decades and decades of therapies of like, this is exactly what we want. If you want to make a machine that makes this, this is what we're going to ask for. And as far as I know, teeth are not turning into cylinders and cubes anytime soon. So you need a machine that could not work on pure arcs. You need machines that could work in like splines or basically any kind of curvature that you want and bend it out. And then the technicians, they're going to a digital workflow, but they should be thinking like they were before. You shouldn't go and say like, hey, you need to just change the way you're thinking and think like a CAD operator. That's like, and that's the antithesis of useful, because technology should be bending its way to work for you, not you should be bending your way so that you can work with the machine. And you shouldn't be limited by templates or predefined, like, this is what it is, now push it to what you want. Why don't you just draw exactly what you want? From a quality level, it should be as good as your best craftsman. Because if not, like, what's the point, right? And you're not going to be able to attract customers by saying, yeah, it's kind of crappy, but it was much cheaper for me to make, right? Because you're like, oh, people are really hard to hire, and look at my profit and loss sheet. You know, I really need to make this more efficient. Like, I'm sure you're friends with your customers, but they don't care, right? That's your problem. So it has to be as good as your best technician. It has to be consistent regardless of which technician uses it. And it has to not require this master craftsman to babysit it, because that means you still need the master craftsman. And beyond that, I think these things, the way they're, where they should be going, personally, this is where I think we should be going, is that many labs are starting to use lab management software or ERPs or MRPs, and every click that we can get rid of, the better. Could you scan a barcode and it loads the file and orients it correctly, and you could just say this was the script, and it just sort of like pre-populates it as much as possible. Because if you're doing hundreds a day or 100 a day, and you know, oh, it's only 5 clicks, well, that's 500 clicks just today, just for one person. So we should just eliminate every click. And a lot of this stuff, of course, is going to the cloud. And I just know this from all the medical stuff that we do at Pensa. If you're going into the cloud, you just got to be sure that it's HIPAA compliant, because this is patient data, it's private, and the FDA cares, right? So like, it has to be hardened against any sort of security risks. So I can tell you from our equipment, since it's going into aerospace, you can air gap it, because like, the military does not want our equipment attached to their network. So you should think about that. That might be important to you. But also just integrating it into whatever workflow outside before and after the equipment is used, I think could be really important, because you might say like, boy, it'd be really great if it could just talk to the input, right? And talk to the output. This part was made, let's add it to the tracker. And then that sort of brings up the point of like, what's your total time that you are saving? Sure, we're saving per part. Maybe, you know, I've even heard today 25%, 50%, maybe more. That's just the design. What about the output? How fast was it to bend? Well, what if did you have to sit there and adjust it? Because that's time. Did you have to switch tooling? How long did that take? Did you have to calibrate it after you switched the tooling, or you switched the spool? How long did that take? Do you have pneumatics? Because pneumatics require filtration, and they require maintenance and oiling, and who knows how to do that, and who's really good at repairing that? Do we need the one guy who knows how to repair the machine? And then what about customer support? Because you want to minimize the downtime. Stuff will break. Mechanical stuff loves to break. It just will. Everything has a life. So what happens? It will break. Is your lab shut down? Is it like we've automated everything and now nobody knows how to bend anything, and now the one machine goes down? Or Microsoft has that one update that shuts everything down, and then like, who are you going to call? Can you call those people? Will they answer? Will they be there? So this true productivity comes with the sum of the entire workflow. So look at any piece, including the 3D printers, including the mills, including the vacuum formers and the trimmers. Look at it all and say, how much time and money does it take as a system, right? And it's not useful if it takes too long, the output needs rework, or the setup interrupts the flow, or skilled operators are still required. And the lab actually needs things that are like parts per day, consistent, no matter who the operator is, reduced time, useful parts, and anybody can use it. So some people ask us like, well, what will happen to my team? You know, am I replacing everybody with robots? And the reality is, no, it's actually quite the opposite. So this is called the Jevons Paradox, which is the cheaper you make something, you would think that it'll just now be cheaper and it'll be easier, right? We've made a dishwasher, now we've freed up our time, we can do nothing but read books. And we know that's not true. So when they came out with like word processing, we're like, oh, typewriters are dead and paper will be used less and there will be less typists, and nothing was further from the truth. We've used more paper than ever because you can just press print because it's cheaper to make. It's cheaper to use, and you don't have to imagine the days of the monks, right? You have one piece of paper, like that's all you want. But now we're just like, get a couple of reams because we're blowing through it. So the more things get inexpensive, the more the classic one is the ATM. That the number of tellers went up. They thought the ATM would bring a bunch of teller jobs to the ground, but it's not true. It's because the bank was cheaper to run, and maybe we didn't need 5 tellers in one bank, but we needed 5 banks because now the bank is so cheap to run. And this is true of AI. Like AI will take our jobs. No, it's actually so cheap. That's the paradox. And this, of course, happens all the time in manufacturing. So again, in Pensa, we use CAD all the time in machine and 3D printers, CNCs, everything. And the 3D printer runs full tilt practically. We have a bank of them. They never stop because we're printing whatever. Every product you can imagine, we probably worked on it. And this has lowered the cost of iterations and productions, so we end up doing more iterations and more production. So so manual has a cost, is very flexible, like you really can't beat the human. But automating also has a cost. So part of this is like, well, what does it really cost? So there's the equipment cost. Software has a license. There's the wire costs. And can you use your wire, any wire? Can you be competitive and pick the wire that you want? There's maintenance, upgrades. There's tooling. The tooling is a wear component. Guides are a wear component. There's labor and training costs. There's unanticipated downtime and what that might cost you. And then support cases. But what does it unlock? It should unlock an increased throughput. It should unlock a reduction in operational risk. Namely, like you've got that one key employee, can't retire. I mean, I know a lot of you guys use musicians, I hear, because they're really good with their hands, but what if the band gets really good? You never know. They're gonna be big. Mom is gonna be proud. And what does it unlock? Does it unlock new revenue potential? Does it unlock new shapes, new types of products that you can sell? New ways to think about the product, new ways about downstream implications? It's like, well, now this is automated, this might be easier than to embed it in the acrylic, or what happens to the rest of it, and how do you grow? So the general equation, right? I like math. Labor savings, right? Plus increased throughput, reduced training costs in general, and then CapEx and OpEx below. So if you're getting a 1, you're at break even. For some, break even might be pretty good because it's break even, but I've reduced my risk, right? But if it's better than 1, then you should do that all day long. I mean, think about it. I'm excited if the bank gives me 1%. So I think it should be better than 1.1 or 1.01. But this is just a way to frame it, right? And then, so one of our customers, you guys probably know this customer, but I didn't want to put their name on it, but these machines are printing me money. And he's kind of right. So Neolab has a couple of our machines. So I just thought I'd give you some kind of case studies. I asked them, give me some pointers, tell me what's been going on. So he said it's a game changer. We spend less time training, 20 to 50%, right? Productivity, so he said like, well, we were going to train this person in manual bending. We would anticipate that in 3 months she should be able to produce maybe 10 retainers. I said, how'd it go? She said, well, the first day she was able to produce 15 that were useful, sellable, and we were ready to go. And in 6 months, people are producing 35, 40 a day, right? There's new onboarding fits naturally into the old training system. They don't need new training manuals. They don't need a manual. And it complements the skills and the talent that they already teach, right? So this is the Jevons Paradox. They had 2 CAD designers. Now they have 5 in one year and change. And they get 2 more coming, which is to say that the robots actually created more jobs. This one is my favorite. He says the co-op student runs the bender. He produces over 100 parts a day. That means the intern is producing 100 parts a day, which is to me insane, right? Because the master craftsman now could be just the intern, which kind of puts like, they're fungible. It puts the fun in fungible, right? The CAD side, he says we hire gamers because anyone who can operate a mouse can operate the machine. And you know, talent is difficult to find. And they have 3 new benders in 8 months. So it's increasing because the demand is there. So what is automation without regret? This is just sort of like a summary slide of everything I gave you, right? One is you should ask on any of this type of equipment, not just wire benders, and I'm not saying we're the best, it's not a sales pitch, but what you're looking for, right? 3D printers for sure. I've bought a lot of 3D printers that are doorstops. Does it reduce training time? Can I make a wide variety of parts with it? Because that really unlocks a lot more. Do I need a master craftsman to fix everything? Do I need a skilled technician to maintain it and its mechanics? Because now I have this new thing. Like I have a CNC machine. It takes a skilled operator to run. It takes a different skilled operator to maintain it. And that's why it's unplugged. Brooklyn real estate, very expensive. And this thing is not small. Can I use any wire I want? That means any size, any material, any supplier. Do I have to change the way I work? Which is, like, do you have to bend the way you're doing things so that you can just squeeze something out of the thing, right? How many types of jobs can I automate? Which is kind of interesting because then you can say, well, I can automate this wire. That means I can automate this wire, which means I can automate that wire, which is something that we saw a lot at Neolab, right? They first start with 3-to-3 Holley label bows, and they're like, oh, wait a minute. But you could do springs and rests and TPAs. And so it's like, oh, if it can do that, then you could do this. Will this automation improve the quality across any user, right? Will it increase the throughput without adding to the headcount? If you're adding to the headcount, it's because you've had more demand, because you can produce stuff faster, better, cheaper, right? And when things go wrong, how fast can I get support to get it back up and running? Because one thing that we've noted, of course, is that these things become critical. Like when we first started out with those two little cute machines I showed at the beginning, those were for schools. If they kind of didn't work, the kids got, they pulled out the popsicle sticks. It was like pretty low bar. But this is like, these things are, if they're printing money, the printer better work, right? And then what's my ROI? What's my break even? What's my better than break even? And what does it unlock in my business? That's the approach I would look at any automation equipment. How did I do for beers? Look at that, only 30 minutes. Do you guys have any questions, comments, disagreements? This is like a group of 8th graders. Nobody asks questions. What's that?
We're just easy.
Yeah, just easy. Yeah. I mean, maybe it was so explanatory.
They want to go to happy hour.
Yeah, that's probably true too.
Does the machine, is it able to bend a perfect curve if that's what you're prescribing it, or is it following it?
We can do both, but we would more likely bump bend it, but the bumps are so close together that you can't tell it's not bump bend. But we can roll bend, but the roll bending, the wire is very, it doesn't have a lot of buckle strength, like it'll buckle. So it doesn't like the resistance of roll bending. Whereas we will roll bend, aerospace parts, like bigger stuff, because it's got column strength. So really we bump bend this thin wire, but the name of the game is the density of bends. Yeah.
How often do you have to change the parts, and how much are they?
So for our equipment, we warranty the tool for at least a year. It should last a lot longer. If not, give us a call. We're pretty good about it. The cutter will wear, but your wire is so thin. Actually, thin wire has an interesting counterintuitive problem that it dents the cutter, right? If you ever use a normal pair of snips on your wire, you'll notice you've just thrown out that pair of snips because it just dents it. So the thin wire actually creates a very hard, sharp point. But our tooling is what, 2,000 or something?
2,400.
2,400, but not all of it breaks.
Yeah, so the bend head I think is only $800.
Yeah, so it's maybe 800. And that's usually because the little tiny pins like bing will eventually, they're so hard, they break in a brittle fracture, like a glass. But it should outlast.
And this one's straight wire, right? It's not on the spool?
This one works on straight wire, and this is just our philosophy, is that garbage in, garbage out. If you put an arc in, then I'm bending a retainer onto an arc, and then you're like, why is it more closed or more open? It's because there was an arc there of which I've now added another shape on top of that arc. So it's critically important to have arrow straight wire. And in our experience, the more we try a spool, there's two issues. One is to get straighter wire, you need full hard. And when you get full hard wire, we get complaints that it doesn't feel the same under the pliers and it snaps in the mouth, and then you get returns. So there was a request for 3/4 hard wire, which does not come off straight in the spool. So we get it pre-straightened, and we get it pre-straightened in the factory that makes straighteners, because it's like such an annoying lost art of how to get a straight wire. And it's because it's so counterintuitive. You're like, well, a couple wheels go this way, a couple wheels go that way. How hard can it be? And then you run it and you're like, it's not really that straight. And so we get the guys who actually make the straighteners to tune it, and they have this set up, and it's like really long, and it's very fussy.
That's kind of interesting because I knew an orthodontic technician, and he bent all his wire off the spool just like the European labs do.
Yeah.
And I could never get used to that because I always wired them straight. But again, the concept behind it on a spool is that you would use less wire.
Yeah, there's less waste.
You wouldn't have all these little pieces of wire that you couldn't use anymore.
Right. So we make 4-foot lengths wire. So lab length wire is 14-inch wire. You can probably get like one wraparound and change out of that. And so we make 4-foot lengths. You get like 10 out of it, and you waste about this much.
So you can throw like Elto wire, flexible wire in there?
You can. I can't tell you that I've tested the crap out of that. I've tested the crap out of 304V.
Elto is cobalt chrome.
Oh, cobalt chrome? Yeah, we've done cobalt chrome. I think the stuff that probably wouldn't work is like braided. I would think that would twist. Yeah, I don't think that would work. Nitinol, tie-dye, tie-dye, they're all different brands, but they're all nickel titanium. Nickel titanium really wants to be straight. So we can move it, but it might come back straight. So we get that a lot in the eyeglass industry because they use a lot of that stuff. And aerospace for satellites. We've had our equipment, just a little fun side. I got a call, they're like, so I'm here at Jet Propulsion Laboratory, and we've got your equipment on a zero gravity simulator, and it's going to steer the spacecraft, because if you bend the wire this way, the spacecraft goes that way. And I'm like, we accounted for gravity most of the time, but we can account for zero gravity if you want us to. But yeah, so we can steer a spacecraft if that comes up in space. For the new moon, Artemis 3. Somebody's going to need a retainer up there.
What's the process of going from like an 032 wire to an 040?
That would probably, so our rule of thumb, and it's really just truly a rule of thumb, is about 10% of the wire diameter. We try to keep it optimized. So in other words, if you say, I'm definitely going to use 040, we're going to make an 040 tool. And then you could put a smaller thing in there, but over time it's really kind of wiggly in there. So your shapes, the sharpness of the bends are a little bit off, and they're a little bit elliptical. And yeah, I mean, if you're under a microscope, but you'll notice it in other ways. So 040 to 036, you're probably good, but 040 to 032, that's a little far. I mean, it doesn't look that bad when you hold it in your hand. So like today we were running 032, and then we'll make an Adams class out of 028, and that's fine. You just pick whichever wire you want. So that's the other advantage. So the nice thing about spools is the waste and the one-time setup. What's not nice about spools is the one-time setup, because you're like, oh, this particular case, 2 parts that are 032 and 2 parts that are 028. It's like, I'm gonna have to disassemble the spool. That's a good 2 hours. Forget it, we're gonna hand bend that. So in ours, you just like pick the one you want, run it, put the next one in. Or if they're 48-inch sticks, run a bunch of the 032 parts, put the 028, run a bunch of 028 parts, don't change the tool. We hope to get you out of the trough of disillusionment, if you know.
Are there limits to the, like on the small size, to the size of the loop that you can bend?
Yeah, so if the tool is optimized for the wire, so if you're running 040 and you have 040 wire in there, we can get a real tight loop in there. And then the diameter of the wire usually sets the smallest loop I can make. I mean, I can make a smaller loop, but you're not gonna like it. Because what happens is, you want an arc, which is completely visual, because that's what's traditionally done by hand. But the computer wants to make a polygon, like a hexagon, or an octagon, or tenagon. And so we bump it a bunch of times so much that you can't tell the difference that it's not a polygon. But if you get a really thick wire, very small loop, you're gonna get like a half hexagon. And you're like, yeah, it works, but I don't like the look of it.
It works better with thin wire then?
Well, it works with either one. It's just that like 040, like 032, we'll do a 5mm loop. So it's like 200 thousandths parallel, and any length you want. And then we can go smaller, 4.5. So that's, sorry, I'm metric. 180. Well, you're Canadian. Metric. Yeah, you're go metric system. So let's go all metric. So in 0.8 wire, we can do 5mm loops, 4mm loops, 4.5. You just pick the size. But if you say I want a 3mm loop in 0.8 wire, it's probably going to be a little bit polygonal. But that's a really tiny loop. But if I do a 1mm wire, like, I'd have to see, what can I get? Can I get a 4mm loop out of that? Maybe. Because the tool die is bigger for 2 reasons. One is the wire will, if I give you a really sharp die, it cracks the wire. And then the other reason is the strength of the die. I don't want the wire to be, between the fight of the die and the wire, the die's got to win over thousands of parts. So we need a little bit of strength because it's super hard. We were making little tiny balls out there. They're really kind of fun if you want to see how small you can get. You get these little itty bitty things. You're like, oh, maybe I can make jewelry. I'll have a little side gig, Etsy shop. I hope the framing was sort of helpful because it's kind of like where my world is sort of crossing Venn diagram into your world. But beer clock. All right. Thanks, guys.